We swim in it, breathe it, yet rarely give it a thought. Nitrogen, an element so commonplace, so seemingly inert, that its very ubiquity masks its profound importance. It's the invisible giant of our atmosphere, constituting nearly 80% of the air we breathe. But far from being a passive bystander, nitrogen plays a dynamic and essential role in the very fabric of life. Imagine a world without proteins, the building blocks of our bodies, or DNA, the blueprint of our existence. This is a world without nitrogen. From the vibrant colors of a butterfly's wings to the silent growth of a redwood forest, nitrogen is the unsung hero, quietly orchestrating the grand symphony of life. Its journey, however, is anything but passive. It cycles through the air, soil, and living organisms in an intricate dance of transformation and exchange. Understanding nitrogen is akin to understanding life itself, a journey into the fundamental chemistry that shapes our planet and ourselves. Life, in all its diversity and complexity, relies on a delicate balance of elements. Carbon provides the backbone, oxygen fuels the fire, but it's nitrogen that adds the spice of life. Proteins, those workhorses of the cellular world, are built upon a framework of amino acids, each one intricately woven with nitrogen. DNA, the molecule of heredity, carrying the code for life from one generation to the next, also depends on nitrogen. The four bases that make up DNA's alphabet, adenine, guanine, cytosine, and thymine, all rely on nitrogen for their structure and function. Without nitrogen, there would be no genetic code, no passing on of traits, no continuity of life as we know it. But nitrogen's role isn't confined to the building blocks of life. It's also essential for the very processes that sustain life. Enzymes, those biological catalysts that speed up chemical reactions, often rely on nitrogen-containing molecules to function. Chlorophyll, the pigment that allows plants to capture sunlight and convert it into energy, also has nitrogen at its core. In essence, nitrogen is woven into the very tapestry of life, from the smallest microbe to the largest whale, a testament to its fundamental importance in the grand scheme of things. The discovery of nitrogen is a story of deduction, of carefully teasing apart the components of air. In 1772, a Scottish physician named Daniel Rutherford conducted a seemingly simple experiment. He placed a mouse in a sealed container with a limited supply of air. As the mouse breathed, consuming oxygen and releasing carbon dioxide, the air inside the container changed. Rutherford then removed the carbon dioxide by reacting it with a solution of alkali. What remained was a gas that extinguished a flame and, more importantly, did not support the life of the mouse. He had effectively isolated nitrogen, though he didn't fully grasp its significance at the time. Initially called noxious air or phlogisticated air, nitrogen's true nature as a distinct element was later confirmed by other scientists, including Antoine Lavoisier, who gave it the name azote, meaning without life. Ironically, this name belied its crucial role in supporting life. The discovery of nitrogen, though seemingly serendipitous, opened a window into the invisible world of gases and paved the way for a deeper understanding of the chemistry of our planet and beyond. Step into a lush forest or a verdant field, and you're witnessing the power of nitrogen at work. Plants, the primary producers of our planet, rely heavily on nitrogen for their growth and survival. But there's a catch. While nitrogen is abundant in the atmosphere, it exists in a form that's largely inaccessible to plants. Atmospheric nitrogen, or N2, is a very stable molecule, with two nitrogen atoms held together by a triple bond. Breaking this bond requires a significant amount of energy, more than most plants can muster on their own. This is where the magic of nitrogen fixation comes into play. Certain types of bacteria, known as nitrogen-fixing bacteria, possess the remarkable ability to convert atmospheric nitrogen into a usable form for plants. These microscopic alchemists reside in the soil or, in some cases, within the roots of certain plants, forming a symbiotic relationship. Through a series of complex biochemical reactions, these bacteria break the strong triple bond in N2 and convert it into ammonia, NH3, a form of nitrogen that plants can readily absorb. It's a silent partnership, a microscopic dance between bacteria and plants that underpins the productivity of our ecosystems. Section 5. From explosives to fertilizers. The discovery of nitrogen's power extended beyond the realm of nature and into the hands of humans, for better or for worse. In the early 20th century, two German chemists, Fritz Haber and Karl Bosch, developed a process to artificially fix nitrogen, converting it into ammonia on an industrial scale. This breakthrough, known as the Haber-Bosch process, revolutionized agriculture and warfare. Ammonia became the key ingredient for synthetic fertilizers, providing farmers with a way to boost crop yields and feed a growing population. However, this process also had a darker side. Ammonia is also a precursor to nitrates, which are essential components of explosives. The Haber-Bosch process, initially hailed as a scientific triumph, became a double-edged sword, fueling both the growth of food and the devastation of war. The irony is stark. The same element that nourishes life could also be used to destroy it. The legacy of the Haber-Bosch process is complex, a testament to the power of human ingenuity and the unintended consequences that often accompany it. Section 6. The dark side of nitrogen. Nitrogen, the giver of life, also has a darker side, a consequence of its own success. The very same properties that make nitrogen essential for agriculture have also led to its overuse and, ultimately, its pollution of our environment. Synthetic fertilizers, a boon to food production, have become a major source of nitrogen pollution. When excess nitrogen from fertilizers enters waterways, it triggers a cascade of ecological consequences. Algae, those microscopic plants that form the base of aquatic food webs, thrive on nitrogen. An influx of nitrogen from fertilizers can lead to algal blooms, choking waterways and depleting oxygen, creating dead zones where fish and other aquatic life struggle to survive. Nitrogen pollution also extends to the atmosphere. Nitrous oxide, N2O, a potent greenhouse gas, is released from agricultural soils and livestock operations. This gas traps heat in the atmosphere, contributing to climate change. Furthermore, nitrogen oxides, NOx, emitted from vehicles and industrial processes, contribute to smog and acid rain, impacting human health and ecosystems. The challenge we face is to harness the benefits of nitrogen while mitigating its negative impacts. Finding a sustainable balance is crucial for the health of our planet and future generations. The challenge of nitrogen pollution is not insurmountable. Just as human actions have disrupted the natural nitrogen cycle, we have the capacity to find solutions and restore balance. One promising approach lies in precision agriculture, a data-driven approach to farming that optimizes fertilizer use. By carefully monitoring soil conditions and crop needs, farmers can apply fertilizers more precisely, reducing waste and minimizing nitrogen runoff. Cover crops, planted during fallow periods, can help prevent soil erosion and absorb excess nitrogen, preventing it from leaching into waterways. In addition to agricultural practices, technological innovations also offer hope. Researchers are exploring ways to develop nitrogen-efficient crops, genetically engineered to require less nitrogen fertilizer. Others are working on alternative methods of nitrogen fixation, mimicking the efficiency of nature's own nitrogen fixers. Addressing nitrogen pollution requires a multifaceted approach, involving farmers, scientists, policymakers, and consumers. By working together, we can harness the power of nitrogen while protecting the health of our planet. Nitrogen's influence extends far beyond the farm and the environment, permeating our daily lives in ways we might not even realize. Take a deep breath, and you're inhaling nitrogen with every gulp of air. Look around you, and you'll find nitrogen in countless everyday products. The food we eat, often grown with the help of nitrogen fertilizers, is packaged and preserved using nitrogen gas to prevent spoilage. Our cars rely on nitrogen-filled tires, providing a smoother ride and improved fuel efficiency. Medical professionals use liquid nitrogen for cryosurgery, a procedure that freezes and destroys abnormal tissues. Even the dazzling colors of fireworks displays owe their brilliance to nitrogen-containing compounds. Strontium salts create the vibrant reds, copper compounds produce the brilliant blues, and barium salts give rise to the shimmering greens. Nitrogen, in its various forms, is woven into the very fabric of modern life. From the mundane to the extraordinary, nitrogen's presence is a constant reminder of its versatility and its essential role in our world. Nitrogen's story extends far beyond our planet, reaching into the vast expanse of the cosmos. It's a key element in the universe, forged in the fiery hearts of stars. When massive stars exhaust their nuclear fuel, They collapse under their own gravity, triggering a supernova explosion. These cataclysmic events scatter elements like nitrogen into the interstellar medium, the space between stars. Over time, these elements coalesce to form new stars, planets, and even life itself. The nitrogen in our bodies, the air we breathe, was once part of a distant star, a testament to the interconnectedness of the cosmos. Scientists studying the atmospheres of other planets and moons have detected nitrogen in various forms. Titan, Saturn's largest moon, possesses a dense atmosphere composed primarily of nitrogen, with traces of methane and other hydrocarbons. Understanding the role of nitrogen in the universe provides valuable clues about the origins of life and the possibility of life beyond Earth. As we look to the future, the story of nitrogen becomes increasingly intertwined with the fate of humanity. With a growing global population and increasing demand for food, the need to produce food sustainably and efficiently becomes paramount. Finding ways to optimize nitrogen use in agriculture, while minimizing its environmental impact, will be crucial. Researchers are exploring innovative approaches to nitrogen fixation, seeking to develop more efficient and environmentally friendly methods of producing nitrogen fertilizers. Genetically engineered crops, tailored to require less nitrogen, offer another promising avenue for sustainable agriculture. Beyond agriculture, the challenge lies in reducing nitrogen emissions from industrial processes and transportation. Investing in renewable energy sources, improving fuel efficiency, and developing cleaner technologies are essential steps towards mitigating nitrogen pollution and its impact on climate change. The future of nitrogen is ultimately in our hands. By understanding its complexities, embracing sustainable practices, and fostering innovation, we can ensure that this essential element continues to support life on Earth for generations to come.